Thank you for the wonderful talk. Now we have to have the next talk. So next one, the second speaker is Dr. Alessandra Bertoldo. She is a full professor of biomedical engineering in the Department of Information Engineering, University of Padua. Her presentation title is The Brain Dark Energy Puzzle: How Strongly is Glucose Metabolism Linked to Resting State Brain Activity? Unfortunately, she is unable to attend this meeting in person, so we will play the video recording. Thank you very much.
Thank you for being here to hear this presentation. I'm Alessandra Bertoldo, and I don't have anything to disclosure. This presentation deals with the investigation of the relationship between three important brain signals, one related to glucose consumption, one related to neural communication. Why we select these two signals? Our brain has a high energy cost compared to the consumption required by our organs. Roughly 25% of glucose is used by the brain in face of only 2% of its body weight. This energy is spent in rest, with similar numbers also for cerebral flow and oxygen consumption. This so-called dark energy of the brain in neuroscience, and it's thought to be largely employed for maintaining resting potentials and some threshold synaptic transmission, since most of the energy budget of a neuron is utilized at the level of synapses rather than in the neuron's body. On the other hand, fMRI board is a signal used to investigate the brain network and to study the interconnected brain regions that communicate with each other to support various neural processes behavior. Based on these considerations, regional differences in brain metabolism should be well explained, I repeat, by variability in spontaneous activity as what can rise from fMRI board signal investigation. Okay, so brain glucose consumption can be assessed in vivo by using positron emission tomography scanners and specific tracer called for deoxyglucose FDG, and can be used in two different modalities. One modality is static modalities, by which we can just derive a 3D vision of the glucose consumption throughout a semi-quantitative measure that is called SOVR, or we can investigate in dynamic way the glucose behavior inside the tissue, the brain tissue specific, and obtain more several quantitative measures. Resting state network can be investigated by using, of course, fMRI signal that is, well-known signal by which we can obtain several different types of information. One of them is functional connectivity, but of course we can obtain also feature from the signal itself. So the questions that we want to highlight are, which is the spatial link between FDG, so glucose and body resting state? Is visually sensitive to different biological descriptors of glucose consumption, so it's different linked if I use SOVR in comparison to other descriptors of a glucose behavior, or this is this link better described by including also CBF as similar to information. So first, we start with the SOVR. That is the simplest way that we have to visualize the glucose consumption in some indirect way. So we using a semi-quantitative measure. And we can visualize the spatial distribution of SOVR that is not homogeneous, but we can appreciate the regions having higher SOVR and regions having lower SOVR. So there is a spatial distribution and the spatial identification of a glucose behavior. This is a vector analysis showing you the SOVR at the voxel level, it will be the same at the cortical level by using parcellation, and C is showing you the level of SOVR for cerebellum and subcortical areas. So from fMRI, we derived 50 different descriptors, and we recruited this descriptor in descriptors of a single self. So like, for instance, region homogeneity and the alpha, the amplitude of low frequency fluctuation, together with the family medium and standard deviation of the both single self. We can derive also the descriptor HRF. We can derive the features describing the functional connectivity, static functional connectivity. So summarizing the depth of the standard connectivity by using a graph-based metrics like the degree, strength, the cluster transmission, and so on. And we can also deal with dynamic functional connectivity, have a pool of functional connectivity along a time interval, and describe the mean, strength, the mean degree, the standard deviation of this measure, or the entropy of this one. So in total, I repeat 50 different descriptors. The descriptor, sorry, I'm going back, show also, part of them show to have a high collinearity. So in order to solve this collinearity and to select really in some well-defined way the best descriptors of the SODR, we used a mixed factor modeling approach with a specification, more than one specification approaches, and the final model is composed by 9 features. Just only 9 of the original 50 fMRI-based features were selected as the best to describe the SODR behavior, the spatial SODR behavior at the group level. This approach was repeated in 2 different data sets, independent data sets, and the results is exactly the same. So the 9 features were exactly the same for both the first and the second data set. And the interesting is that in any case, the average R-squared value is roughly the 55%. So just only, or it's a lot, I don't know, it depends on the point of view. 55% of the variance of the SUVR is linked, is expressed by the modeling, the combination of the 9 features. And this is the best that we can do, consider of course the 50 original fMRI features. What is interesting and important to highlight that in any case, even if 9 are the features, the most prominent is the most important in both datasets is regional homogeneity, so REO. And REO itself explains the 50% of the variance, average of 50% of the variance. So it's absolutely for both datasets the most important parameter in describing the link between glucose and fMRI. This in any case is just an average value because the model is better, is capable to better describe the link in the gray pulsars, while it performs worst in the blue and the red areas, in the red pulsars. So there is a heterogeneity also in the possibility of these 9 features in explaining the variability of the SODR throughout the subjects. So for this first step, despite the variability of a large number of features, the strongest and most consistently selected predictors of glucose metabolism came from local properties of the board signal, such as the temporal aspect of a signal and local synchronization, and not from a functional connectivity and not from dynamic functional connectivity. We thought that regional homogeneity is important because it might reflect underlying features of interregional suborganization, including architectural features, which are known to differentiate the primary sensory motor areas. Regions interesting with high SODR remain unexplained by most resting state functional features, and correlation increased when assessed across nodes with lower metabolic consumption. So there is a sort of non-linearity also in this model that we would like to understand it to be better. Very meaning question. Meaning question are what is something that is, there is a link, the link is different. If it's stated to use SVR, a link different would FDG based features, and this, we can improve the description by using also not only fMRI but also see blood flow and SMRO2 values. Again, the workflow is more or less the same. So we wanted to, the support point is FDG, so the glucose, and we wanted to increase the interpretation by using some additional information coming from different path tracer, but giving us the information of the CBF and CMRO2. Again, the plane, the picture, the correlation between the pictures remain of course the same, speaking about the fMRI, and the last two rows are reporting the link of the CBF SMRO2 with the remaining features. The links is very low, so meaning that these two features are giving us different information considering the previous fMRI features again. So if you wanted to give a look at just to the additional information, so the K1, that will be what we wanted to now state to use as a VR, we wanted to interpret the K1, so the glucose inflow, comparing the glucose inflow with facing the glucose inflow with a 50 fMRI picture plus the 2. After we repeat the modeling, consider the K3, so the glucose phosphorylation step, and after the Ki, that is the overall glucose uptake, combining K1, K2, but also K1, K2, and K3, and is the overall glucose take, considering both the glucose information coming from the blood into the tissue and the glucose phosphorylation. So here is just only a spider plot to consider one by one the correlation of the K1, Ki, K1 in yellow, K3 in green, with the different features, the 50 features for fMRI plus the 2 for CBF SMRO2. And again, there are some interesting correlations just only with the senior features. So interesting correlation with SMRO2, a little bit lower and expected with CBF, but nothing really interesting and no interesting correlation with features coming from dynamic functional activity, some with static functional connectivity. So this is just a one-for-one pairwise correlation, nothing to with the model, and applying exactly the same model, but with a K. This is the Ki, this is K1, this is K3. The impact of the feature is exactly the same. So the most important feature remains in the description of the behavior of the spatial organization, spatial distribution of this of a Ki, overall glucose consumption, K1, just only the relation between the velocity of the inflow of the glucose and the K3, the phosphorylation step, is based on the, again, just only the real. The R2 is higher with the Ki, so this is the model is really good, the best in comparison with Ki, K1, and K3 is perform better with the Ki as a second level with the K3, and lastly with the K1 is not very good because the medium possibility to over the medium value of R2 is roughly 0.15 for Ki, while here we are close to 0.35. So, and this again is the impact of the model is the best in the gray areas, while performing not really well in the red and the blue areas for Ki, K1, and K3. What's happened when we add the second features? So the CBF and CMR2, CBF is not selected as to be as an important feature in describing neither Ki, K1 or K3, but interesting is there is a large impact of SMR2 and improving ability in describing the Ki when we use also SMR2. And SMR2 is quite important also in describing K1 and is also important, but less in comparison to K1 and less in comparison of K1 in describing the K3. I repeat, K3 is really the phosphorylation process. The glucose is transforming glucose phosphate. So, and again, also in this case, the impact and the ability of the model is a variable and is better in the parcel here highlighted in gray color. Okay, so answer, because we have to conclude this presentation, the strength of spatial association between CBF and CMR2 and FDG based on Ki or K3 was somewhat weaker when expected, especially for CBF. Nevertheless, the combination of fMRI variables and CBF and CMR2 led to a highly satisfactory Ki spatial description. So we reach also 80% of explanation of the variability at the group level and roughly 45% at the individual level. And combining direct hemodynamic and metabolic information for CBF, CMR2, in particular CMR2, CBF is not really so important. I remember CMR2 are absolutely important. The information on spontaneous brain activity provided by the Ball signal explains a large portion of individual level variance in glucose metabolism. So this is to repeat to answer the last two questions. So I conclude. Thank you for for being here, and I want to thank, of course, a lot of people in Italy, but also outside Italy, in particular, of course, Tommaso Volpi, that was the first author of the two papers that I presented here in this talk. Thank you again, and see you.